LTI system yt, when you consider x of t as an approximation in terms of pulses, then you have to consider the response in terms of those scaled individual pulses. Okay, so you have to consider the impulse response. So for example, wherever this pulse is occurring, for example, this pulse occurs at k delta. Okay, and you see the pulse duration over here is delta. It's a finite duration pulse, and if you multiply this with the signal x tau, okay, this is x tau, h tau of t, where this pulse is occurring at t equal to tau. So your output is will be the summation of all these individual pulses. So for example, over here, this, if you're considering a very short duration pulse where delta is approaching to 0, then that means, and you're summing up all the responses, right? So for one pulse, for one such pulse, the response is xk delta hk delta of t. So you see this subscript k delta is the same which is present in the argument of the input signal. So that represents the time. So this is the time where this pulse is occurring. This k delta is the time where the pulse is occurring. Okay, and this becomes the weight of the impulse response. Okay, this impulse response is the response to the system. So okay, you have an LTI system. So what's happening over here is like this, as such. You have the continuous time LTI system, and the response of the function delta of delta t minus k delta is the response is denoted by whatever is the impulse you feed at k delta, which happens at k delta. The response is written as the subscript k delta, okay, k delta of t. Okay, so basically what you are doing is you're summing this up. So for each such and if you scale this, if you scale the input by x k of delta, if you scale this input by x k of delta, the output is also scaled by the same scalar. Okay, that happens to be the amplitude of the signal at this instant k delta. And if you are going to apply many such scaled pulses, what it means is that we are going to, so let's sum this up. There will be many such scaled and shifted pulses. So this is xk of delta. Okay, this is the argument of the input signal multiplied by delta of t minus k delta multiplied by delta. Okay, then that means the output, this is my input. Okay, the output will be, and this, let's call this an approximation x hat of t. Okay, so the output y hat of t will be the sum of all such individual scaled impulse responses. That means y hat of t will again be a summation of the same having the same weights xk delta multiplied by the corresponding impulse responses wherever these delta functions have occurred. Okay, and then you sum it up. This is following from the property of superposition, or the linearity property of the systems. Okay, so you have to sum them up from k in general, from minus infinity to plus infinity. So summations are over k. Okay, but as the limit the delta approaches 0, the summation on the right hand side of the above equation becomes an integral. So as can be seen graphically in 2.16. So what it means is that if you have to sum up all these pulses of very short durations, then the natural extension of you can't go sum up all such infinitesimally small duration pulses. The natural extension is that the summation becomes an integration, which represents the area under the shaded region. Over here, this is the, so if you are going to take the area of this, okay, with respect to dk delta, okay, then you see you can take this this basically represents the response of the system to one pulse. Okay, and in order to accumulate all the such responses, this is yt, and accumulate all such responses, you have to carry out the integration from minus infinity to plus infinity to account for all such pulses. This is just one pulse. Okay, but to count for all the pulses, you have to integrate this from minus infinity to plus infinity. So specifically in 2.16, the shaded rectangle represents one term on this summation. This is only one term for at k delta on the right hand side of the above summation. But as delta approaches 0, the summation approaches the area under x tau, ht of tau, as viewed as a function of tau. Therefore, you have to integrate this from minus infinity to plus infinity to get y of t. Okay, so if you are considering this limit where delta approaches 0, then you forget about this summation. It becomes an integration. Okay, and this becomes x of tau, and this becomes h of tau. Okay, this is t. Okay, so this becomes an integration, and then overall k, or this should happen from minus infinity to plus infinity. You have to consider the entire area. Okay, so that means you have to multiply the signal x tau multiplied by the impulse response wherever this pulse occurs. Okay, and then you have to integrate it. So whatever is the area under this, and then you have to account this for all such instants where this pulse had occurred and corresponding impulse responses, and then you have to integrate from minus infinity to plus infinity to have the output yt. Okay, now since the input xt can be represented as in terms of the shifted and scaled pulses, that is, we can intuitively think xt as the sum of weighted shifted pulses where the weights of the impulse delta t minus tau is x tau d tau. Okay, so x tau d tau forms basically the weight of the shifted impulse. So with this interpretation, the following equation represents the superposition of the responses to each of these inputs, and by linearity the weight on the response ht tau to the shifted impulse. So basically ht tau is the response to the shifted impulse, and it also is going to have the same weight x tau d tau. So then it comes the same weight x tau d tau. Okay, over here you also notice the same thing. X tau d tau is the weight of the impulse response, and that impulse response is basically occurring at t equal to tau. Okay, so the above equation represents the general form of the response of linear systems in continuous time. Now, if in addition being linear, the system is also time invariant, then that means if this pulse, this is the response. Well, remember this, ht of tau is the impulse response of the system, LTI system. Now, if it is also time invariant, so what we are considering over here is an impulse delta which is occurring at t equal to tau. So we can write this as t minus tau. Okay, and the response was h. The subscript is denoting where this pulse has occurred. Subscript is at tau. Okay, this is a function of t. So this is the impulse response of the shifted pulse. Well, what we are going to do is we are going to drop this subscript, and we are going to write this as tau of t as h naught of t minus tau. Okay, and well, in later on we are going to drop this subscript naught as well. So over here you see the response of LTI system to the unit impulse at t equal to tau, which is shifted by tau second from the origin, is similarly shifted version of the response to the unit impulse delta t. Again, for notational convenience, we'll drop the subscript and define the unit impulse ht as h naught t. Okay, so basically the response will be h of t minus tau. Okay, that means if delta t is applied to the system, the output is ht. Okay, the output is ht. Then if the system is time invariant, okay, for LTI system, for time invariant system, then of course your impulse response is also going to be delayed by the same interval tau. Okay, because since this impulse is applied at t equal to tau, well, the impulse is also going to, the response of the system is also going to come after tau seconds delay. Okay, given the system is also causal, right? It can't come before tau. So therefore, ht is the response to delta t. In this case, the following equation becomes yt is x tau ht tau, and then you just drop this subscript over here, and you can express yt as in terms of ht minus tau, and this is the famous convolution integral. Okay, and basically you're considering the yt again as the superposition, or call it the weighted, the sum of all the weighted impulse responses, shifted impulse responses, weight scaled and shifted impulse responses, and you have to consider the area under that curve because this is continuous time functions of time. Okay, so the above equation is referred as the convolution integral or the superposition integral. Why superposition? Because the system is linear. Okay, so you have to consider all these area under the pulses, okay, from minus infinity to plus infinity, and you can't sum them up, so you have to consider the area under the curve, whichever whatever is there when you multiply. So this integrand is basically, we are considering the area of this integrand as a function of time. This is x tau ht minus tau, and basically how you evaluate this is that for a given LTS system, just flip the impulse response at the origin, and then you start shifting this for t greater than 0, and then multiply it by the signal xt, and just compute the area under the curve and do it from minus infinity to plus infinity. That represents the area. That represents the area as well as the uh, area of the curve x tau ht minus tau and the output yt of the system. Okay, so the superposition integral is the continuous time counterpart of the convolution sum, correspond to the representation of a continuous time LTS system in terms of its response to a unit impulse. So the convolution of two signals again will be symbolically represented by an asterisk sign. This is not a conjugation. I mean, the conjugation in the text is also written the same way as the superscript, but this is again the notation used for convolution integral. Note that this notation is also used, we have chosen the same symbol to denote both discrete time and continuous time convolution, but the context will be sufficient to distinguish between the two cases. Okay, so if again this is if this is discrete time, then instead of t you're going to have discrete time indices. Okay, but this convolution is going to show you this asterisk sign shows the convolution operation between the two signals.